In this video, I want to derive the second pair of Maxwell's equations, and I will follow Landau's book on the classical theory of fields. And in this case, we are going to consider the action as written in a more general form, in particular when we consider a system of particles, so we have more than one particle. And in particular, in this case, when we have more than one particle, the action can be written in this form. So we have the action, and we can write it symbolically like this. So minus, in this case, I have to sum over all the actions of this kind, integral mc ds. So here this summation is performed over the number of particles, so over the particles. And then I have a similar summation, and I have a term like this, E over C A mu dx mu. And then I also have another contribution. So in particular, I have another contribution which is related to the electromagnetic tensor F mu nu. And in Gaussian units, this can be written as minus 1 over 16 pi c integral F mu nu d for x. In this case, I have to integrate over the 4 volume because of the dimensions because of the units of F mu nu. And we are going to transform this integral in a similar fashion. So we will have an integral over d for x. Whereas the variation of this integral here, so when we take the variation of this first integral, we get 0. Why? Well, because in this case, in order to find the field equations, we assume that the motion of the charges is given, and we only vary the potentials. On the other hand, to find the equations of motion, we assumed that the field was given, and we varied only the trajectory of the particle. And in that case, we were considering only the action related to one particle. But never mind, so I said that this term here will be disregarded when we take the variation. Let's rewrite this second term here. So the summation of integrals of this kind, E over C A mu dx mu. In order to rewrite this expression, let me first rewrite it like this, integral dE over C A mu dx mu. So in this case, I have simply rewritten the charge. Instead of the charge being discrete, I have rewritten it in terms of an infinitesimal quantity dE, and then of course we have to integrate also over the charge here. So the element of charge can also be written as the charge density rho multiplied by a three-dimensional volume dV. So this dV here can be written as d3x if you want. So it's dx1, dx2, dx3, whereas d4x, can be written as dx0, which is c times dt, and then I have dx1, dx2, dx3. Now we are going to write again this integral here. So this one can be written as integral rho over c a mu, and then I'm going to write dx mu like this. So dx mu over dt, and then I have dt times dv. dv comes from dE, so dE is equal to rho times dV. But now dt times dV is equal to d4x divided by c, divided by the speed of light, because if you remember, d4x also contains the speed of light. So we have c dt dv, and therefore dt dv will be d4x over c. So this can be written as integral j mu, where j mu is simply equal to rho times dx mu over dt. So this is like a 4 velocity. It's very close to a 4 velocity. We have dt here. For a 4 velocity that we defined as u mu, it was dx mu over ds. So this was u mu. But in this case, we have rho times dx mu dt. This is the 4 current. And then I have a mu, and then I have to divide by c squared, and then I have d4x, like this. Now, when we take the variation of the action, ds, we can write it as minus integral of j mu over c squared, and then I have dA mu. So when I take the variation will not vary j mu, because as I said earlier, we assume that the motion of the charges is given, so we are not going to vary this density here. We are just going to vary the field. So we have dA mu, and remember that the variation of this term here was also 0. The variation of that is 0, because as I said, this is still related to the motion of the charges. And then I have plus 1 over 8 pi c. If you recall, we had 16, not 8. But now let me tell you why. We will get 8 in a moment. And then here we have f mu nu, variation of f mu nu, d for x equal to 0. Now, I have used the fact that df mu nu times f mu nu plus f mu nu df mu nu. So when I take the variation of the product of f mu nu with f mu nu, this is what I actually get, but it's easy to see that this is equal to twice f mu nu variation of f mu nu. It's very easy to show if you contract these tensors with the metric tensor, the Lorentz metric. And then I can also substitute here. We know that f mu nu can be written in terms of this tensor here, a mu. This is the 4 potential. So f mu nu is related to the derivatives of a mu. So ds can be written as minus integral 1 over c, then here we have 1 over c, j mu dA mu plus 1 over 8 pi, then I have f mu nu, and then I'm going to rewrite this variation like this. So we have the derivative with respect to x mu of the variation of a nu, and then I have minus a similar term 1 over 8 pi f mu nu, and then I have derivative with respect to nu, x nu, variation of a mu, and then I have d for x, and then we will set this equal to 0. But now you can check that this expression here, these two terms, can be added together, and I can get minus 1 over 4 pi f mu nu, derivative with respect to x nu, delta a mu. So basically this term is equal to this one. It's easy to check because you can, for example, change here in this first part, this term here, you can change mu to nu, and then you can change nu to mu, and then you can easily see from that, for example, if you rewrite this as minus f nu mu, and you do what I just said, so if you change nu to mu and mu to nu, and you can do that since these are all dummy indices, you will get that the expression will be equal to this one. So you can rewrite it like this. Basically, this one multiplied by 2. And that's why I have a factor of 4 here. Then what I'm going to do is I'm going to integrate this second term, so this term here, by parts. And if you do that, delta s can be written like this, minus 1 over c, integral, and then I have 1 over c, j mu, plus 1 over 4 pi, df mu nu, dx nu, and this multiplies delta a mu, d for x, and then you have a boundary term here, which comes from the integration by parts. So if you integrate by parts, this partial derivative will be here, so it will be applied to f mu nu. So the sign changes here due to the integration by parts, and then this boundary term will vanish because at the boundary, so at infinity, the fields are 0. And then here we set this equal to 0. Finally, we find that since all these variations here are independent of each other, we can set this equal to 0. And from here we get df mu nu dx nu equal to minus 4 pi over c j mu, which you can also write as df nu mu dx nu equal to 4 pi over c j mu. So in this case we are using, as I said at the beginning of this lecture, we are using units such that they are Gaussian units. And what do I mean by Gaussian units? Well, it means that basically the constant epsilon 0 is equal to 1 over 4 pi, and mu 0 will be therefore equal to 4 pi over c squared. So if we define epsilon 0 like this will be a consequence of the fact that epsilon 0 times mu 0 is equal to 1 over c squared, right? So you can choose a unit system such that this is true. And why is it convenient to write the equations in terms of this system? Well, because, for example, if you take a look at this, you see that 4 pi times epsilon 0 is equal to 1. And this is particularly convenient when, for example, you deal with the Lorentz force or you deal with the Coulomb force. Because in the Coulomb force, when you have just one particle, you have something like this. You have a charge, Q or E, whatever you want to call it, and then you have 4 pi 0 in the denominator, and then here you have R squared. And of course, if 4 pi epsilon 0 is equal to 1, then this expression will simplify. So it is just convenient because of that. It's just a choice, and it's not really important. What really matters here is the proportionality between this derivative and this for vector, this for current. This is another pair of Maxwell's equations, and one can work out those equations, but I don't want to do it here. I have done it in previous sections where the units were different, but never mind. So we found exactly the same thing, and we're going to start from here next time because I want to show you something different from what I showed you in the previous sections. We're going to dig deeper into the theory of classical electromagnetism, and I want to show you something very interesting that is not usually seen in basic courses on this.